My name is Michail Athanasiou, and I'm a senior postdoctoral researcher at Fourth Institute in Greece, laboratory of Professor Spiros Yiannopoulos, who is also the leader of Work Package 1 in the emphasis project. My scientific background lays into the field of electrochemistry. In recent years, I have focused on the development and optimization of supercapacitor based on laser-derived graphene electrodes. Within the framework of emphasis project, Fourth is leading the production of high-quality three-dimensional graphene and graphene nanohybrid electrodes. We are also soldering the complete physicochemical and electrochemical characterization of these electrodes, while we are also providing with these electrodes our partners to test them in a larger scale, for example, Peony, and with their in-house electrolytes like University of Würzburg and so on. Fabrication of laser-assisted graphene is an emerging method for using high-quality graphene electrodes for energy storage application. Now, in the emphasis project, we emphasize the use of simple, low-cost lasers, which are actually used in welding and cutting industrial applications. We are able to produce high-quality turbostratic graphene via a single step by irradiating suitable biomass precursors without using any wet chemistry or conventional slurry-based techniques. This avoids the use of hazardous solvents and their associated waste products, as well as binders that can compromise the final electrode performance in terms of electronic and electrolyte ion electron conductivity and electrolyte ion diffusivity into the pores of our electrode. Finally, these laser-based synthesis methods are easily upscaled to a larger roll-to-roll process and can take place under ambient conditions, making the entire process very simple and cost-effective. As with any newly introduced process, these laser-assisted production methods of graphene and graphene nanohybrids from biomass precursors faces some challenges. The first is that the final mass loading of the active material is in the low rates, sometimes is close or even below to 1 milligram per square centimeter, which may negatively affect the final area capacitance performance of our electrode. This is more pronounced in case when we are using the LEST method, where we are actually able to synthesize high-quality graphene flakes and simultaneously transfer them to the current collector. Right now we are working on the particle size of the biomass precursor powders we are using and with the laser settings in order to achieve higher loadings. Secondly, the success of the laser methods depends on the ability of the precursor to absorb the specific wavelength of the laser irradiation. In addition, also a higher content aromatic rings is required in the precursor chemistry in order to be this precursor to be converted in a high quality graphene. These requirements, especially when we are using biomass precursors, make imperative to us to introduce thermal pretreatment step to our whole process in order to precarbonize the precursor and also to increase its aromatic content. This is more evident in the case of lignin biomass we use. We are trying to introduce as low as we can mild treatment where is required and which could be easily applied in a case of a future roll-to-roll process scale-up.